You see AI doing these incredible things, right? But what's stopping it from just going completely off the rails? How does it find real patterns in the world instead of just getting lost in random noise? Well, the answer is this fundamental concept called regularization. It's the unseen force, the essential guardrail that makes AI actually work. And today, we're going to pull back the curtain and see exactly how it does it. So here's how we're going to break this down. First, we'll tackle the data dilemma. Then we'll look at the really elegant solution. After that, we'll see how the theory actually turns into a network, explore how we can learn from unlabeled data, and finally wrap up with why regularization is so absolutely key to everything. You know, every single machine learning project kicks off with the exact same problem. You never have enough data. You're trying to figure out some universal truth from just a handful of examples. It's kind of like trying to predict a whole movie from just one single frame. Mathematicians have a term for this. They call it an ill-posed problem. Right. Think about it like this. Let's say you're trying to draw a map of a mountain range, but you only have 3 data points. How do you connect them? Do you draw a straight line, a nice, gentle curve? Or do you draw a wild, spiky, jagged line that perfectly hits every single point? The thing is, there are literally infinite ways to connect those dots, and almost every single one of them is going to be wrong. And that is the exact dilemma an AI faces. So in the world of math, for a problem to be well posed, a few things have to be true. A solution has to exist, it has to be the only solution, and it has to be stable. But with machine learning, because we have such limited data, we almost always fail that second test, the uniqueness test. There's just not enough information in our training examples to point to one single perfect answer. And what happens when the model has all that freedom? It tries way, way too hard. It twists itself into that crazy, jagged line, perfectly nailing every data point it's ever seen. But by doing that, it's not learning the real underlying pattern. It's just memorizing the random noise in the data. We call this overfitting. And believe me, an overfit model is completely useless when it sees something new. Okay, so that's the problem. How on earth do we fix it? Well, to fight back against this overfitting chaos, we introduced this brilliant mathematical idea called regularization. And here's the absolute genius of it. We just change the rules of the game. We tell the model, look, your goal isn't just to minimize your mistakes anymore. That's the empirical risk part. We add a counterweight to the scale, a complexity penalty. We're now explicitly telling the model, hey, don't just be accurate, be simple. And that little dial in the middle, lambda, lets us control that balance perfectly. This slide just perfectly shows you the power of that lambda dial. If you turn lambda way down, you're basically telling the model to ignore complexity. It gets obsessed with the data points, and you end up with that overfit, jagged mess. But if you crank lambda way too high, the penalty for complexity is so huge that the model is too scared to learn anything at all, and you get an oversimplified, useless line. The real art is finding that Goldilocks zone, that sweet spot right in the middle. Now, this is so important. Regularization is not magic. It can't just create new information out of thin air. What it does do is inject a prior belief into the system. It's an assumption, and it's an assumption we humans use all the time. Occam's razor. The simplest explanation is probably the best one. Regularization is just the mathematical version of that. All right, so we've got this powerful mathematical idea, but how do we actually build something with it? How does this theory about cost functions and penalties actually translate into the nuts and bolts of a real machine learning model? Well, the answer is surprisingly direct and, frankly, really beautiful. Here's where the math leads us to something amazing. When you actually solve the regularization equation, you find that the best possible solution isn't some random, complicated curve. It's actually built by taking these simple, smooth bumps. They're technically called Green's functions. Placing one right at the location of each of your data points and then just adding them all up. Think of it like a little democracy. Each one of your data points gets to cast a vote on what the final curve should look like, and that vote always has the shape of a simple, smooth bump. The whole learning process is just about figuring out how much weight or influence each of those votes should have. You sum up all those weighted votes, and voila, you get a final model that's perfectly smooth and still respects all the data. And this process, it doesn't just give us a theory. It literally gives us the blueprint for a specific type of neural network. It's called a regularization network. What's so wild is that its structure isn't just some random design. The hidden layer has exactly n nodes, one for every single example in your training data. Each of those nodes, is one of those smooth bumps we were just talking about. It's this beautiful, direct line from pure mathematics to a real-world network architecture. Okay, so this whole framework is really elegant, but it's got one giant catch. It needs labeled data. And in the real world, getting those labels, having a person go through and tag every single image, for example, is the single biggest bottleneck in all of AI. It is slow and it is expensive. The truth is, the vast majority of the world's data is unlabeled. So this brings us to one of the hottest areas in modern AI, semi-supervised learning. You've got this tiny little island of precious labeled data sitting in a massive ocean of unlabeled data. The billion-dollar question is, can we use that ocean to help us out? Can the actual shape of the data itself, even without labels, guide our learning? The big idea that lets us crack this problem is called the manifold assumption. It's this belief that even when your data is in some crazy high-dimensional space, like the millions of pixels in an image, the important stuff isn't just scattered around randomly. It's all concentrated along a much simpler, smoother surface, a manifold. It's like this. All the houses in the world exist in 3D space, but almost all of them are built along 2D surfaces, like roads. If you can learn the map of the roads, you can navigate the whole world way more efficiently. So how do we find these hidden roads in our data? We use this incredible tool called spectral graph theory. Imagine taking all of your data points, labeled and unlabeled, and just plotting them out in space. Then you basically play connect the dots, drawing lines between points that are close to each other. This creates a giant graph, like a huge social network for your data. And by analyzing the structure of that graph, we can find the underlying shape, the main highways running right through our data. We can literally map the manifold. And once we have that map, we can totally level up our original idea. This is called generalized regularization. We still have our first penalty that says be simple in general, but now we add a second penalty. And this new one specifically punishes the model if its answer doesn't smoothly follow the roads we just discovered in the data. So the model is being guided not just by a general preference for simplicity, but by the actual intrinsic shape of the data itself. Okay, let's put all the pieces together. We started with this fundamental data problem, we found a really elegant solution, and then we supercharged that solution using the hidden structure we found in our data. So why does this one concept matter so much? At the end of the day, regularization is the thing that turns machine learning from a brittle academic idea into the robust, powerful technology that's changing our world. It solves that core ill-posed problem by giving our models the constraints they need. It stops them from overfitting so they can actually generalize to new situations. It gives us that crucial dial to balance accuracy and simplicity. And as we've seen, the core idea is so powerful that it even lets us tap into the enormous potential of all the unlabeled data out there. So the next time you use an AI, just remember that there's this invisible hand of regularization working behind the scenes, constantly guiding it away from chaos and towards a simple, sensible answer. At its heart, it's a prior belief that we've deliberately programmed in, a mathematical preference for simplicity. It's our Occam's razor, built for machines. And that leaves us with a really big question. This assumption works incredibly well. So what other fundamental human assumptions are we embedding, right now, into the very heart of our most intelligent machines?